Now it's recording. Let's start. Today we will talk about exact equations and Euler formula to be able to solve differential equations numerically. Okay. So last time we talked about separable equations, linear equations, and autonomous equations, if you remember it. All they had different forms and all they had different ways to solve them. And now we will talk about exact equations and exact equations in that form. There is a function that can depend on your independent and dependent variable x and y. And there is another function like that. And after that, y derivative is coming equals to 0. This is dy dx. Okay, your dependent variable is y, your independent variable is x, and the coefficient of the derivative is can depend on both x and y. Okay. So it can be non-linear. It doesn't matter. To be able to say it is an exact equation, you need to have this m function and n function. And to be able to understand if this equation is an exact, you need to check this equality. Look at that. So you have an equation and you saw that it's an exact equation. It is in that form. After that, to be an exact equation, the derivative of m, the one that does not have a derivative inside, look at that, with respect to y, should be equal to derivative of n with respect to x. If this equality holds, your equation is an exact equation. And if it is an exact equation, you can say that there exists a solution in that form. And what does it say? This solution's derivative with respect to x should be equal to m, and this function's derivative with respect to y should be equal to n. Okay, I know that you don't understand anything. I want to point out again from the beginning very specific things. First, this is the form of the exact differential equation. Okay, mxy plus nxy, y derivative equals 0, or m plus ny derivative equals 0. Okay. And to check if it is an exact equation, you need to take the derivative of m with respect to y. You need to take the derivative of n with respect to x. And if they are equal to each other, then this equation is an exact equation. And if this is an exact equation, what do we say? We say that there exists a solution such that this solution's derivative with respect to x should be equal to m, and the solution's derivative with respect to y should be equal to n. And your solution is given in this closed form. On an example, it will be much more clear, promise. Let's look at it on an example. Let's say that this is our differential equation. Look at that. It's not separable. It is not linear. Remember that linear was y prime plus pxy equals gt, right? Or gx in that case. And separable was we should have separate x and y variables. In this one, no, we cannot do that. So if you look at it, this is mxy. This is a function with x and y. And this is the coefficient xy. Again, function with respect to x and y. So our m is 2x plus y squared. Our n is 2xy. And as you can see, this is the true form. Then I can check that if it is exact or not. How do we check that? We need to check this equality. We should take the derivative of this function with respect to y. What is that? Since this is x, the derivative will be 0. This is y, 2y. And let's take the derivative of n with respect to x, which is 2y. Since 2y equals to y, yes, it's an exact equation. Is it clear so far? Is it clear that this is our m function, this is our n function, so the form is true? Then I can check if it is exact or not by taking the derivative of m with respect to y, and by taking the derivative of n with respect to x, and check if they are equal to each other or not. And exactly this is what we did, and both were 2y. So since they are equal to each other, it is an exact differential equation. Okay, if it is exact, what do we know? We know that we have a solution. How? The solution's derivative with respect to x should be equal to m. What was m? 2x plus y square. Here you go, 2x plus y square. And the solution's derivative with respect to y should be equal to the n. So this is what we know. And we are trying to find what is that solution? What is this phi? We know that derivative of phi with respect to x is equals to that one. Derivative of phi with respect to y equals to that one. But what is phi? By using these two equality, we will find phi, which is the solution of our exact equation. Okay? Is it clear, that part too? Please follow that. Once you understand once, it is easy, but you need to understand once in here. So, how do we do that? Since we know the solution's derivative according to equation 1, we know that phi x is this one. And I want what is phi. And to get rid of this derivative x, this is partial, we need to take the integral of each side. If I integrate this one with respect to x, what we have? We have x squared over 2, 2's are gone, x squared. We have y squared is just a constant, think about that. And once we take the integral with respect to x, this is going to be y squared x. And this is our phi function, plus c. It can be constant or it can depend on a function of y. Because think about that. We are taking a derivative with respect to x. So this is going to be 2x. This is just a constant, so the derivative will be y squared. And if there is a function of y here, the derivative of y with respect to x will be 0. So it can be a constant or it can be a function of y. That's why I need to add this one as f of y. And now this is my solution, but I don't know what is f of y. Now I need to find f of y as a next step. After that, to find f of y, we will use the second equality. We know also that the derivative of this function with respect to y should be equal to 2xy. Then let me take the derivative of that one with respect to y. The derivative of x squared, 0. Think this one is a constant. We are taking partial derivative. And derivative of that one with respect to y, it is 2yx plus whatever this f's derivative. And this should be equal to that one. Then let's compare this one. Let's make it equal. If they have to equal to each other, then the f derivative y should be 0. If it is 0, take the integral of each side. Fy should be a constant. Now you can write your solution as x squared. What was that here? This is the form of my solution. X squared plus y squared x plus c. Now I can say that this is a constant because I compared with the second equation and I saw that f derivative y is 0 and f of y is c. And this is the closed form or implicit solution of my differential equation. Now, do you have a question? Is it clear? Firstly, let me go back. Firstly, I need to make sure that this is the form of an exact equation. Once I did that, I need to define m function, n function. And as I need to check if my equals nx. If that's true, it is exact. Once I make sure that, I know that there should be a solution in that way. The derivative of the solution with respect to x should be equal to m. Derivative of the solution with respect to y should be equal to n. Then, to be able to find this solution, phi, we are using the first equation first. And I am taking the integral of each side. If I take the integral of each side, I will find the solution. But there is one more unknown is coming once I do that. Because once I take the integral, there can be a function of y here. And to be able to find this function of y here, I'm using the second equation. What I'm doing, I am taking the derivative of the solution I found with respect to y, and I am comparing with the second one. And whatever the derivative of f in there, from this equality, I'm finding f. And I'm just plugging in here, and this is going to be the general solution of my differential equation. Okay? Let's look at that one. Here you go. Look at this function. Y cosine x, 2x e to the y, sine x, x square e to the y. So it's a very complicated function. And solving this one is not easy. But with an exact one, it is not hard also. Let's check that out. So if this is m and if this is n, the form is true. I have m plus ny derivative 0. So as a first step, I need to check if it is exact by looking my equals nx. Let's take the derivative of m with respect to y. You are going to assume x is just a constant. So if I take the derivative of this one, so this is going to be just a coefficient. That's why the derivative of y cosine x with respect to y will be cosine x. And in here, 2x is just a constant. Derivative of e to the y is e to the y. So 2x e to the y for the m derivative of y. So n derivative of x, the derivative of sine x is cosine x. The derivative of x squared e to the y is 2x. E to the y is just a constant staying there. Derivative of 1 with respect to x is 0. So as you can see, the right and left is equal to each other. This is an exact equation. So that's good. If that's the case, I know that there exists a solution. And this solution's derivative with respect to x should be equal to m, which is this function. The derivative with respect to y should be equal to n, which is that function. So what we were doing, we are starting by using the first equation. You can start by using the second equation, but to be able to understand, I am just doing the same thing. Here you go. Do you have a question? No? Okay. So I am starting with the solution's derivative with respect to x, and this should be equal to m, and here is your m. So I know that phi x is y cosine x, 2x e to the y. So again, I'm taking the integral. The solution will be with respect to x, y sine x, x squared over 2, x squared e to the y, plus f of y. Again, this has to be here. Now, next question is, what is f of y? And to find f of y, we are using the second equality. So according to second equality, the solution's derivative with respect to y should be n, this function. So I will take the derivative of that one and compare it with this n, okay? So I'm taking the derivative of this one with respect to y, take derivative with respect to y. What is that? Sine x, x squared e to the y should be equal to n. What is n? Sine x, x squared e to the y minus 1. Now compare it. These are gone, then f derivative should be negative 1. If f derivative is negative 1, take the integral of each side. F of y will be negative y plus c. And now I am going back to this solution, general way. Now my solution is y sine x plus x squared e to the y. And instead of f of y, we have minus y equals c or plus c equals 0. It doesn't matter how you write. And this is your solution. Again, is it clear? Sorry. Is it clear? Let me see in here. Okay, great. Now, if it is not exact, what do we do? We are finding another integrating factor. You remember for the what is that, variable coefficient linear equations, we were finding an integrating factor, right? It was e to the integral p of t dt. Last class we talked about that. And for the exact ones, we can find also integrating factor. If your equation is not exact, once you multiply your equation with this integrating factor, your equation will turn back to an exact one. Okay? This is a magical function that turns your differential equation into an exact equation. And how are these equations? I will explain it right now. Make sure that try to understand hard in this one. I know it's a little bit hard without writing, but let's focus on. Okay. To convert a DE that is not exact into an exact equation, multiply it with one of these integrating factors. Why one of these? And how can we choose? Here you go. So one of the integrating factor is d mu dx, my, you know what is m, you are defining at the beginning, minus nx over n times mu. If this right hand side is only depending on x, then you are in the right track. This is your integrating factor. But if you find this function is not only depend on x, there is also a y term, then no, this is not the right one. Try the second one. And what is the second one? Dm dy, d mu dy should be equal to nx minus my over m times mu. Okay, if this function depends only on y, yes, this is your integrating factor. Okay. If none of them is working, you cannot solve this one as an exact one. But if these are working, these are going to turn your differential equation into an exact differential equation. Is it clear? I will show it on an example right now. Check that out. This is a differential equation. Of course, these parentheses is not going to be there. I am just putting it for you to understand. Well, this is going to be there because this is the coefficient of y derivative. But in general, this is coming without. So you need to make sure that this you will define this function as m, this function as n. Okay. The form is okay. Now let's check if it is exact or not. What was the condition? My should be equal to nx. Let's take the derivative of m with respect to y, which is 3x plus 2y. And derivative of n with respect to x, 2x plus y. No, they are not equal, so it is not exact. Okay, we have one more choice. We can find an integrating factor. And there we have two different choices. You can start by trying dm dx. d mu dx should be equal to my minus nx over n. My is this one. Nx is this one. Subtract these. X minus 2x and 2y minus y over n. What is n? Here you go. X squared plus xy. Now what we have in the numerator? 3x minus 2x, x. 2y minus y, y. X plus y. And over, if you factor out by x, these are going to simplify. What you have only a function of x. Yes, it is working. I can find an integrating factor because this function only depends on x. If there would be staying y there, no, it's not working. Then you need to try the second one. Okay. But since this part only depends on x, which is 1 over x, it is working. So I need to solve this differential equation to be able to find my integrating factor. What is that? d mu dx equals mu over x. And this is separable. I can move mu in here, x in there, d mu over mu, dx over x, integrate each side, solve for mu. ln mu, ln x, take the integral, mu x is x. We are not using c here because we will combine the c's at the end. So choose c0 for the integrating factor. So we found integrating factor x. So what are we waiting for? Once we multiply my function with that, it has to turn my function into an exact one because it was not exact. So let's multiply our function with x. What will it be? 3x squared y, xy squared plus x cubed, x squared y, y prime. Now let's check that. Take the derivative of m with respect to y, which is 3x squared, 2xy. Take the derivative of n with respect to x, which is 3x squared, 2xy. See, it is exact. So you can solve this one. Now start from here and solve that. how we were assuming there is a solution where phi x should be equal to n, phi y should be equal to n. We were taking the integral of phi, which is m, from each side, and there were f of y was coming, and for this solution we were taking the derivative with respect to y and compare with that one, and we were finding the y there, and this will be the solution. Please try in here, solve yourself. From there, since this is exact, find your solution in that way. Okay? Is it clear? Integrating factor. I'm checking here. Any question? Okay, great. Once you do couple examples by yourself, please, this is there is a big algebra going on here. So to be able to do it on the time in the exam, you need to get used to doing this algebra. You know, in the exam, although it's gonna be on the Pearson, you need to send back to me the written answers, and I will check your written answers together with the Pearson for the exams. Okay, that's why you need to get used to doing this algebra, and once you start doing that, if you start doing from the beginning, you will enjoy it because it's really nice. I like differential equations a lot between all math courses. Here you go, another one. Nonlinear first order differential equation. Do you have a question? You can stop me anytime. M is xy, n is this function, and you are checking my, derivative of m with respect to y, which is x. Derivative of n with respect to x, which is 4x, 0, 0. So one of them is x, one of them is 4. So it's not exact. It doesn't mean that you can multiply your equation with 4 and it will be exact. No, it's not 4. There is another integrating factor that can make your function exact. And what is that? You can try my minus nx over n, since you already have my minus nx, which is minus 3x over that one. Depends on x and y. It doesn't depend on only x. So it doesn't work. Then try nx minus my over m. So what is the derivative of n with respect to x, which is 4x, minus derivative of n, which is x, over m, xy. 3x over xy, x is argan, 3 over y. Yes, this only depends on y. Then this will be my integrating factor. And what was the integrating factor? dm over, here you go, dm over dy equals that one times mu. And that one we found it as 3 over y. So it is the same as e to the integral 3 over y dy, the one that you were doing. You can do this in that way too, okay? And you can find your integrating factor as y cube and multiply your equation with that y cube right now. X, y to the 4, 2x square y cube, 3y to the 5, 3y cube. And now check that if my equals nx. My is 4xy cube and nx is 4x y cube. See? It is exact now. Now you can solve this one as an exact equation and the solutions will be in that way. Okay? Is it clear? From the beginning, we have been talking about these exact equations and it should be in that form. And what is m? What is n? Okay, great. Once it is exact, you are looking for a solution phi. Great. Let's wait. If you have a question, I want to see. And Once you make sure that it is an exact, what you are saying, there should be a solution phi. How? Phi x should be equal to m, phi y should be equal to n. You are using the first one by defining phi. After that, there will be an f of y function there. Once you find this f of y, you need to take the derivative of that one with respect to y and compare with n. And by this comparison, you will see what is the derivative of f of y. And again, by integrating of each side, you will find f of y. Just update your function and this will be the solution of your differential. Okay? Puzzle. You need to solve step by step. If that does not work, you have another choice, which is the integrating factor. You will be checking this term. This term should be depend on only x, as if you want this to work. Okay, and if it is not working, check that one. If this should only depend on y. Okay, one should work. Okay, I think no question. Please solve this one by yourself and this one by yourself. Make sure that you understand it, because it right now you feel like it is clear, but once you start solving it by yourself, you will understand really if you have a question or not. Okay, so after the classes, since we are doing online classes, the classes are finishing earlier because we are not writing each algebra in here. That's why it takes shorter. So for during time, make sure that you are solving by yourself with pen and paper. It's a nice brain work for, yes.
I have a question.
Sure.
Plus C, in example, plus C is Fy. I remembered. At which condition plus C is become Fx?
So since you are starting from the first condition, this we are assuming there is always a function of y here, because once you what do you say, the derivative of this one with respect to x should be equal to m, right? And
yes,
then if there is a function of y here, once you take the derivative of this one with respect to x, there should be 0. That's why we are saying f of y. If you want to, there will be no f of x if you start with the first equation. But if you start with the second equation instead of 1, then you need to take the integral with respect to y. And in that sense, there should be an f of x there. But if you follow the steps that I did, it will be always f of y here. There will be no f of x.
Okay, thank you very much.
Is it clear?
Yes, clear for me.
Okay.
Thank you.
Because this part is important. En önemli nokta burası. Çünkü burada x'e göre türev aldığınız için y'ye bağlı bir fonksiyonun x'e göre türevi her zaman 0 olacak. Siz birinci condition'dan başladığınızda integrali x'e göre alacağınız için burada hep f of y gelecek. Ama bunun tam tersini de yapabilirsiniz. İkinciden başlayıp birinciyle de kıyaslayabilirsiniz. İkinciden başlarsanız buradaki y türevinden kurtulmak için y'ye göre integral alacaksınız. Bu durumda burada x'e göre bir fonksiyon olabilir diye düşünüp ona göre çözümün türevini alıp onunla kıyaslayacaksınız. Tamam. Ama bunu takip ettiğiniz sürece burada her zaman f of y olacak. I explained things in Turkish just to make sure that. And if you have another question, I can explain in English again and again. It doesn't matter. Okay. I see that all students are Turkish. That's why I think no problem in that right now. Okay. Now we can talk about then Euler's method. Euler's method is a method not to be able to find not exact but numeric solution. Okay. Sometimes some non-linear differential equations we cannot find the exact solution. At that time we are trying to find an approximate solution. Okay. And this approximate solution, one of the way to find this approximate solution is Euler's method. And we know that if f and the derivative of f with respect to y are continuous, then this initial value problem has a unique solution in some interval that belongs to t0, right? We did it by existence uniqueness in the last class. So when the differential is separable or exact, we can find the solution just as we did in the previous courses and today. However, the solutions for most differential equations of this form cannot be found by analytically. So we cannot write our solution in y equals f of x form. So now we need to find ways to approach our solution. And one of the approach is Euler's. And of course, you can draw the direction fields and you can have an idea about the solution. But again, it's not enough for you to have the solution. Okay. And with this Euler's method, we are approaching the solution with tangent lines. Okay. And how do you do that? Here you go. Let's say this is your solution, exact solution. And by starting from some point t0, we can define a tangent line at that point. And what is that tangent line? It is a derivative. And what was the derivative or slope definition? Y minus y0 over t minus t0 is going to give us the slope, right? And exactly by using that, y minus y0 over t minus t0 is going to be the slope. And from this equation, I can write this tangent line as y equals y0 plus f of t0 y0 t minus t0. Once I define that one, starting from t0, let's say until t1. And you can approach this curve with this line segment. And starting from here to t2, you can define another line segment that is gonna be tangent part of the solution. And you can follow this solution by these line segments. And as long as you are getting t0 and t1 close to each other, these line segments are gonna be following your solution very well. And this is how we are using the Euler's method. So we will start with some initial value and we will define these line segments, tangent lines. After each step size, we will be defining these tangent lines and we will try to approach this solution. Okay. So for y1 will be y0, ft0, y0, t1 minus t0. And for y2, instead of 0, put 1. For y3, instead of 1, put 2. So you will find the next y value starting with the initial one. And once you find the next, you can put it in the right-hand side and you can reach to the further point. Okay? We will do iteration like that. This is what we call iteration. So again, once you have y1, you can have y2 by plugged in the right-hand side for y1. And once you have y2, you can have y3. Will go until yn. And you will see that you can reach to the closer solution with the real one by approaching the tangent lines, what we call it Euler's formula. Okay, and this is yn plus 1 equals yn plus f h. H is the step size. And we get it uniform step size most of the time. If it is not uniform, we are calling something else, not Euler. I know maybe it's not clear, but on an example, it will be clear. This is I was telling. For example, after each 0.2, we define the tangent line from 0 to 0.2. After that, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, 0.8 to 1. So maybe our real solution is like this, but our approximate solution is following this real solution. Okay? Look at that one. For the initial value problem, dy dt equals that. y0 is 1. And let's use Euler's method. Step size 0.2. So we will start at 0. Look at that. T0 is 0. It's telling in here. And after that, increase in each step size 0.2. So 0, 0.2, 0.4, 6, 8, and 1. And now, since so our y1 will be y0. What is y0? Which is 1. Plus f0. F0 is plugged in 0 for the right hand side. This is your f function. So I will plug in 0 for t. Okay. And y is 1. So t is 0, y is 1. This is my first values to plug in for the right hand side. Times h is 0.2, it is given. And now I found 1.5 as y1. And by using this 1.15, I will find y2. Because y2 is just increase 1 more for the indices. y1, which is I just found, plus f1, which means that plugged in t equals 0.2, y equals 1.5 for the right hand side, the previous value, sorry. And times uniform step size. H is always 0.2. And the next result is 1.87. And now for y3, plugged in y2, f2, which will be t 0.4, y2 1.87 right hand side times h. Next value. And for the next one, I will be using this one and the step that I just found, which was 0.6. And I will find the next, and I will find the next. Is it clear? Yes, no, maybe. Do you want me to repeat it again? Okay, I got one clear answer. Okay, nice. And if you look at, so this is a linear equation. You can find this one as integrating factor. Put this one into a standard form. Your p is 0.5, e to the pt, which is e to the 0.5t, is going to be your integrating factor. I will multiply my equation with e to the 0.5t, and the left-hand side will be always the derivative of mu of ty. And I will take the integral. Once I take the integral of that one, and this is what I will get, and this will be the solution. And for y01, plugged in 0 for t, make it equal to 1, find the constant k, and this is your special solution for this initial value problem. Here you go. This is your special solution. Okay? And this is your exact solution, and this is our approximate solution that we find. For each 0.2, we found the tangent curve, right? And according to this tangent curve, as you can see, this is the error. The error is increasing with each step size. You can see that the difference between the real one and the approximate one. But it's kind of behaving similar. If you get smaller step size, you can get better approximation. Is it okay? So in this one, if you plugged in 0, 0.2, 0.4, this is what you will get from the exact solution. And this is what we get for the Euler's one. Here you go. Once we compare the errors, you can see that errors are just kind of increasing with each step size. It is, and it just, is said in here because our solution is not linear at 0, 1. Okay. Now we are trying the same one, but now the step size 1, 2, 3, 4, and 5. So our step size is 1 instead of 0.2. And this is when h is 0.1, when h is 0.05. And so it's getting smaller and smaller. And this is the exact one, and these are the approximations one. And as you can see, for a smaller one, it is getting closer to the real one. So if you get your step size smaller and smaller, you can get the real answer better. And this is the percentage error. For 0.1, it is the biggest. for 0.01, it has the smallest percentage error. You can see that. So the deal in this one, you try to get your step size as small as possible to be able to get the real answer. And this is the initial value problem again. Let's do it. Now we are starting from 0, step size is 0.1, and we will apply the Euler's formula when t is 1, 2, 3, and 4. And as you can see, we are starting when t is 0, y is 1, we plugged in, we find y1. By using this, we are finding y2, and it's going like this. And this is the exact solution. Again, by linear equation, you can find that. And here you go. These are the comparisons for exact and approximate y. And as you can see, again, since our solution is not linear, it's exponential. It's at the beginning, it's very close, our approximate solution and exact solution. But when t is increasing, the error is getting increasing. Okay. But as long as you get a smaller step size, the error is going to be less than the bigger ones. See, relative error is 50% in that one. Sorry. In this one, 17%. Because here the step size is 0.1, here the step size is 1. Okay. Just as I said, as if your function is, sorry for that, just give me a minute. Okay. As long as your solution is not linear, Euler's method is gonna work, but the error can be big. If you don't want to get a big error, you need to choose your step size as small as possible. Okay? Do you have a question? These are just some solution curves. And you can see that these curves are all exponential. And if you try to use the Euler's method, again, at the beginning, it will work well. But after that, the error is gonna be higher. Okay? Because these are divergent solutions. I want you to know how to apply an Euler formula for differential equations. If you need it, if you have nonlinear ones that you cannot find the exact solution, you can always use Euler. I will provide you the MATLAB code for the next course. Right now, actually, that's it for me. Do you have a question? I'm waiting for you to have a, Sure, you can ask. Sorry, I did not understand. Your voice is not coming clear. Evet. Hayır atmayacaksınız. Ödevleri atmayacaksınız. Sınavda isteyeceğim sadece çözümlerinizi. Sonra grade dediğinizde şey yapıyor o. Grade'i size verecek. Ben sadece kontrol edeceğim ne kadar zaman harcamışsınız, ne yapmışsınız diye. Ama onun dışında solution'ları, ödevler için istemiyorum sizden. I think my internet is not good. That's why I hardly. Okay, who is controlling my computer? Okay, any question? No. Okay. Then see you next week. Again, as I told you, I will assign your second homework. If you will have any question, because you can try 5 times until you get used to the system. You will have a choice to try, okay? Bye. I'm stop sharing it right now.